let me just review those rules again, okay? Because with multi-loop circuits, that's really all I had planned for today. But if y'all want to do some other stuff too, that's fine. We can do it. But you have a couple rules. The junction rule. The junction rule just says that I in equals I out. And then you have the loop rule. Loop rule says that the sum of the potentials across any closed loop, that's equal to 0. We've seen both of those before when we were dealing with parallel and series circuits. We're just formalizing them for multi-loops. And then as sort of a subset of the loop rule, we have these guidelines. When I'm going through a resistor where the current is in that direction, and if I'm traveling in that direction, then the change in potential is negative IR. And then if I'm going through a resistor with the current in that direction, but I'm traveling in that direction, then the change in the potential is positive IR. So those are sort of the first two guidelines. And then if I'm going through a battery, doesn't matter the direction of the current, only the traveling direction, then the change in potential in this case is positive E, because I'm going from low to high. So it's like my electrons are ramping up. They're gaining energy, like on a roller coaster. Chugga, 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 chugga. Like they're going up to a higher potential energy. And then if I'm going in a battery from low to high, in this case, my electrons, they decrease in potential energy. So delta V is equal to negative of the EMF. Okay? So all the multi-loop circuits are following these rules, writing out the equations and then being able to solve the equations. We did one in class today where we sort of wrote out all the equations, and I printed out all the exams from past years with all the multi-loop circuits that I've given, and I just thought we could work through some of those because your free response question will be similar in difficulty to these. Let me just tell you that there are two ways, I mentioned this in class today, but two ways that I can make this easier, because I have resistors all over the place. It's going to be a system of 3 equations with 3 unknowns, and it's burdensome to work out on the exam. And so there are two ways that I can make it easier. I can give you a circuit, for example, that doesn't have a resistor in one of the branches. And if I don't have a resistor in one of the branches, when I write the equation for the bottom loop, there's only going to be one current in that equation. Let me just show you. Let's say that this is 4 volts. This is 2 ohms. Let's say that this is I2, and we'll say this is I3, right? And then if I write the equation for this, starting here and going in that direction, the equation is going to be 4 minus 2I2 minus, let's say this is 6 volts, minus 6 volts equals to 0. So even though it goes through the section that has I3 in it, there is no I3 in that equation. And so what I do, if I leave a resistor out of one of the branches, then I get equations that are just easier to solve because they only have one unknown in them.
Where is I1?
Oh, I1 I didn't label because I1 would be up here. But I didn't label it because it doesn't come into play in that resistor or in that circuit. All right. The other way that I can make it easier, and I've done both of these, although my most common way is to do it this way, where I just leave a resistor, but you could see either or. The other way would be I'll give you a circuit that has resistors in every branch, like this one, for example, but I tell you one of the currents. So I would tell you, for example, that the current here, I2, is equal to whatever it is, 2 amps. I just tell you what it is straight up. And then if you know one of those currents, then the equations are easier to solve because you only have 2 unknowns instead of 3 unknowns. You'll see that as we're working through these, that some equations give you the answer easier with less math, and if other equations will make it more difficult, that just have more substitution. Okay? Let's look at some examples. I'm going to go to the back of this packet that I sent you. I'm not sure if y'all printed it, but these are just all of the multi-loop circuits that I've given, and you can tell where they're from because it has, most of them have the year that I gave it. So for example, this one was from spring 18. Now this one I want to know what is the current through the 3 ohm resistor. So what is the current right here equal to? Notice that on the right loop there is no resistor. So this is one of those problems that's made easier by having no resistor. First thing I want to do is just label my currents. I'm going to label currents and I'm going to give them directions. I'll call this one I1. I'll call this one I2. And I'll call this one I3. You know, it might be useful for you to just decide beforehand how you're going to label the current so that you don't have to really think about it. You don't have to think about it. You can label the currents however you want. But I understand now it's new that it might be useful for you to say, okay, I'm always going to have the currents go down, or I'm always going to have the currents go to the left. That way you don't really have to think about it. William?
So they can all go in the same direction?
Yeah, they can go however you want them to go. Now you need to understand that I1 is only in this part. Once I come to that junction, it's no longer I1. I2 right here is only in this part of the circuit, and I3 is only in that part of the circuit. The currents always change at the junctions. Now, if I want to know the current through the 3 ohm resistor, the easiest way to do this is to write the equation for which loop? The big one, right. Because if I write the equation for the big loop, I'm only going to have one unknown in that equation. So it becomes pretty easy. So I could write, I want to know what I1 is. I'm going to write an equation starting here and going in that direction. That's going to be positive 4 minus 3I1. I'm going with the current. Minus 12 equals to 0. That's negative 8 minus 3I1 equals 0. And so I1 is equal to 8 divided by 3. 8 divided by negative 3, so it's negative 8/3. And 8/3, that's 2.7. Now, I1, on the free response, I'll ask you for the direction and the magnitude and the direction. So you would write, okay, this is 2.7 amps up. Because I had chosen down, but then I found that I1 is negative, and so it needs to go up. Yeah, William?
Why was the 12 volt included in the I1 is supposed to be for the current where it runs?
I wrote the equation for the big loop. That's the equation for this loop right here. And the 12 volt battery is part of that loop. You can apply the loop rule to any closed loop. In fact, you know what? Some you can do. If you have, we don't do this because it's not terribly useful, but if you have a circuit like this, I can apply the loop rule to this loop. Some of those potentials has to be 0. Or I can apply the loop rule to this loop. I mean, we do that anyway because we say that this potential has to equal that potential. We've been doing that all along. So any closed loop. Does that answer your question?
Yes, basically I1 is not a closed loop, it's just an open loop.
Right. It has to begin, the loop has to start and end at the same point. Let's do another one. I have another one that's like the second way. There we go, number 37, 36, and 37. In 37, I tell you that I2 is 0.17. and I say it's to the left. So now I've told you, oh, well, this one's easy actually, because I don't have a resistor too. I want to know what is the magnitude of I3. Oh, no, it's not that easy. So now that I have I2, in order to find I3, well, how am I going to find I3? Because you notice there's no resistor in that bottom loop. And so when I write the loop rule for either the big loop or the bottom loop, no I3 in that. So how the heck am I going to find I3? Right, I'll find I1, and then I have I2, and then I know from the junction rule that at any particular junction, the IN, that's I1 plus I2 in this case, is equal to I3. So if I want to find I3, I need to find I1 and I2. All right, so knowing I3, knowing I1, I want to find I want to find I1. So I can do, well, let's do the top loop right here. And so I can say, I'll start here, I'll go in this direction. Notice I have arrows here for the currents. I will not give you arrows for the currents. You'll have to figure them out. Now, if I give you a question like this, I will tell you the actual direction of the known current, in which case you should label the direction of that current in that direction, because that is the known direction. Like I'll give you the right answer if this is the type of problem I give you. So anyway, let's follow this loop rule. Starting right here, going in this direction, plus 3 minus 2I1 plus 5 plus 6I2. And that's equal to 0. Now, I know that I2 is equal to 0.17. So I get 8 minus 2I1. What's that? 0.6 plus 1.02 or something? 1.02, let's just call it 1. And that's equal to 0. So I1 is equal to negative 9 divided by negative 2, or 4.5 amps. Is that an answer? Huh. Oh, no, that's I1. So now I want to know what I3 is. That's what I'm asking for. So I3 is equal to I1, which is 4.5 amps, plus 0.17 amps. And that's 4.5 plus 0.2, which is 4.7.
I1 was, which thing is not, negative 9 or negative 2 was again?
Oh, this is equal to 4.5. And so up here, this is I1 plus I2. I2 is given to you, and I1 I found to be 4.5. Now remember, if you calculate I1 to be negative, then you put in a negative 4.5 there. You always keep the sign until you get to the very end. When you get to the end, that's when the sign goes away as you're determining the directions. So our answer here would be I1 is I3 rather is 4.7 amps to the right. That's a little more difficult problem, but it's certainly doable for the free response because it's, it's a double problem. Probably, like you'll encounter a problem that's more like this, one that's just a step more difficult than the one that we worked the first time. William?
For question like 36, how do we...
Okay, that's what I want to look at next.
How do we tell where the circuit is traveling?
I'm about to show you. So, number 36. Any questions about 37, Brent? Okay, it's to the right. Because
At that point.
Yeah, so at the point at on this part of the circuit, I've chosen the direction here to the right. You're going to have to choose the direction yourself, but that arrow said I've already chosen the directions for you, and since it came out positive, it's going to be in the same direction. If it came out negative, it'd be to the left. Okay, that's a good point. It's not to the right because it's positive. It's to the right because it's positive, and that's what it's the same as what you chose. Okay? And remember what I said too, that if I have a circuit that is, what's that, landscape, then you don't say left, right, you say up or down, up, down, like that. And if it's portrait, then it's going to be left, right. It'll be either portrait or landscape. I guess I could do it diagonally, but I don't know why I'd do that. Just to be a jerk, I guess.
It'd be easier to
Yeah, I know.
say it clockwise or counterclockwise?
You could, yeah, you could say clockwise, counterclockwise.
Okay.
That's fine. Like, if you want to say that, that's fine. I'm okay with that. Except I, too, is not clockwise, counterclockwise. Right.
Right.
It's just either left or right. But yeah, if you want to say I1 here is counterclockwise and I3 is clockwise, I won't count that wrong. That'll be just fine. You can't say up or down, because here I3 is up, here I3 is down. Like you only get half credit if you give that.
So that's where you just go to the side. I would say for the top one, it would be to the left.
Right, I1 right here is to the left, I2 to the left, I3 to the right. Oh no, yeah, so no, these are up, down, down.
So they can't be referred to as up or down.
When it's in landscape, when I've taken the circuit, like the one on the right, and shifted it so that it's in a landscape. Because I can't say left or right. Like notice here, on this loop, like if I say that it's to the left, it is to the left there, but it's to the right here, so that doesn't really make any sense. Don't worry, on the question, I'll say, is it left or is it right? Is it up or is it down? I'll make it clear. I won't sweat it. Or if you want to be honoring and say clockwise or counterclockwise,
I understand it, because if you were to take like I3 to the right, it can't be to the left because that would be I2.
right, yes.
In that circuit, it wouldn't be.
It would never go to the left.
It wouldn't be I3 no more, it would be I2.
That's right. Yeah, that's another good point. Okay, and students sometimes miss this, that I have three distinct currents. I have a current here, I have a current here, and I have a current here. And those are all three different currents. Let's look at number 36 and erase all this stuff. Oh, check that out. That's cool. I didn't know that. The equations. We're going to do this in class on Monday, but give you a preview. We've already done it, but I'm going to ask you, you'll have a question like this in the multiple choice where you have to, I'll give you a series of equations and you have to figure out which one is right or wrong. And so the way I lay these out is you look at the first number, like let's look at A for example. It starts with -6. All right, well I only have one element in the circuit that could give me a -6. And it's this battery right here. And then I ask myself the question, well, what direction can I, well, this one's the right answer actually, so what direction can I go in order to make this negative? So that tells me that I need to be going in this direction. That'll give me -6. So that gets me started. I come up here, my next is plus 2I1. Okay, that's correct so far because I'm going against the current. And then I should have a -3. Oh, and I do. That's -3. And then I come back. So that one is the right answer. Well, let's look at these others. 5 minus 6I2. That's starting here and going in that direction. I know that because it's a +5. And then I also see the 6I2 right after it. So I'm going in that direction. +5, that's correct. I'm going from low to high potential. -6I2. Oh, that's not right. That should be a +6I2 because I'm going against the current. and then minus 6. Okay, that's right. So the only mistake here is that negative 6I2 should be positive 6I2. It says I2 plus I3 is equal to I1. We've already written the junction rule, and that ain't the junction rule, right? Because the input and outgoing currents are all wrong. 3 minus 2I1. 3 is starting right here, going in this direction. 3 minus 2I1. So far, that's okay. Plus 6I3. This is a common mistake that people see the 6 right here and assume that it has an I3. But that 6-volt is a battery. It's not a resistor. So this is wrong because that I3 shouldn't be there. Not correct. And then 3 minus 2I1. Okay, 3 minus 2I1 plus 5. So far, okay. That should be plus 6. So that should be plus, and the 1 should be a 2, not a 1, in order for that equation to be correct. You will have a problem. It'll probably be the same circuit that you have in the free response, where I give you a series of equations. That'll be good because you can look back at the work you did on the free response and say, oh, okay, well, I've already written down the correct equation for this. I can double check my work here. Okay, where you have a circuit like this and you have to pick out the right equations. All right, let's look. Well, as for I2, in this one, we are looking for I2. How would you find I2? What loop would you use? Top, bottom, or big?
Top.
Okay, let's try using the top. I hear you. That's not the right answer, but let me show you. If I use the top, let's start right here. I would have 10 minus 4I1 plus 2. What's that? Plus 3I2. And that's equal to 0. Now I'm looking for I2, but in order to know I2, I have to know I1. So I can solve that. I'd have to have more information. What's an easier way to find I2?
Do the bottom because it doesn't have a resistor.
Right. I do the bottom loop because there's no resistor in the bottom section. Okay, so if I write that equation, let's start right here. Is that minus 3I2? Minus 2 plus 4. That's equal to 0. And look, I can solve that. So minus 3I2 is equal to negative 2, so 2/3 amps. So I2 is 2/3 amps to the right. Oh, sorry, left, not right. To the left. Because it came out I2 is equal to 2 divided by 3 amps. It's positive, so the direction as shown there is correct. Yeah.
So it starts, the current starts out as positive and then turns negative after it goes through the resistor. I'm just trying to understand the logic of the signs.
Okay. There's no, there is a physical reason, but don't think of it as a physical justification for the signs. It's really just some guidelines that we use in order to determine, is this a positive or negative change in potential. If I'm going with the current, it's negative. If I'm going against the current, it's positive. Don't try to give it a physical reason, right? Because it's not really physical. It is physical, but don't really try to force it into that.
Just trying to understand because I said earlier that whenever a current travels through a resistor, the sign reverses.
No, I didn't say that.
Like for equations.
I didn't say that. When you're going with the current, you have a negative change in potential. When you're going against the current, you have a positive change in potential.
Well, I was referring to like the equations, like which equations are correct.
Okay, yeah, I'm not sure.
I can do that test.
All right, let's do it. Can we do another one? Oh, look at this one. This could be a good multiple choice question. Which is appropriate application of the junction rule? So I have a bunch of different junction rules here. This isn't a circuit that we've done, right? Like we've never done a circuit with, what's that, 1, 2, 3. There's like 5 or 6 different loops in here. But I can still apply the junction rule. So for example, my junction right here should be I5 plus I2 equals I4. Oh, I guess that's the right answer. Yeah, so that is the right one. But look, I can look at some of these others. Right. I2, that's incoming, incoming, outgoing. So I2 plus I5 equals I4. Or I could take this junction. This junction should read I1 plus I5 plus I3 equals 0. Because they're all outgoing currents. Well, let's look at these. I4 plus I6 equals I3. Where's 4 and 6 and 3? Okay, yeah, it's right here. I have I4 and I3 coming in, so it should be I4 plus I3 equals to I6. And that's why that one's not right. I2, 5, and 6 equals I5 and 4. Okay, I don't have any junctions where 4 wires are coming together, so C can't be right. There's no point where 2, 6, 5, and 4 are all together. There's a point here where 2, 5, and 4 are together, but 6 isn't at that junction. So that one's not right. And I2 plus I6 equals I1. That would be right here. I1 and I6 are coming in. And that's equal to the outgoing current, which is I2. I would expect a question, something like that, where you have some wires and you have to figure out what is the outgoing current, or show which of them is a correct representation of the junction rule, just like you have some with the loop rule. Let me show you another one that's simpler. Oh, here's one, number 32. 4 wires meet at a junction. So draw a little picture. The first wire carries 4 amps into the junction, so 4 amps coming in. The second carries 5 amps going out. The third carries 2 amps going out. And so now I want to know, what is the fourth wire carry? Well, I got 7 amps going out, but just 4 amps coming in. So that fourth wire carries what? 3 amps. And it has to be going in. Oh, not that one. D. Okay? You want to do this one again? Are the equations correct? Yeah? All right, so I have option A. I just start with the first one and then step through them. The first one might be correct. I just randomized the options, so just because it's first doesn't mean it's necessarily correct or incorrect. Anyway, 10 plus 4I1. That means that I'm starting up here because I have the 10 and then the 4I1. And the 10 is positive, so that's correct so far. Except the 4I1 should be negative. You'll follow me? I'm going with the current. Plus 2, that's good so far. Minus 3I2. That would be correct if this were positive. It should be positive because I'm going against the current. So A is not correct for 2 reasons. Those 2 signs are wrong. B, 2 plus 3I2. That's starting here and going in this direction. 2, 3I2. That's good so far. And then coming around, minus 4. That one is correct. B is the right answer. I1 plus I3. Take a junction. It should be I1 plus I2 equals I3. So that one's not right. And then 4I1. that's right here, plus 10. So I'm starting here and going in this direction. I have positive 4I1 going against the current. That should be minus 10, right? Should be minus 10, and it should be minus 4. So that one's not correct. And then I want to know what I1 is. In this case, in order to find I1, the easiest way is to take the big loop. And if I take the big loop right here and write my equation, starting here, going in this direction, that's 10 minus 4 I1 plus 4 equals 0. That's I1 equals negative 14 divided by 4, negative 4. That's 7 halves, that's 3.5 amps. And that will be to the left, or 7/2 to the left. A. Yay? Yes? That's okay, William?
So what essentially determines the whether the resistor is positive or negative?
If you're going with the current, when you go through a resistor, the change in potential is, what is it? It's negative. If you're going with the current, the change in potential is negative. If you're going against the current, the change in potential is positive, positive IR. Is that what you were asking?
Yeah, that's what I was trying to ask.
Okay. You want to write down those rules, those 4 little guidelines, put them on a Post-it note, put them on a note card, paste it to your mirror or your cabinets or whatever, and you want to internalize those. They will become internal to you. They'll eventually just be second nature, but you want to make sure that you know those simple rules.
Recognizing those rules is one thing, but recognizing it is another.
Okay. Well, you got to know them first, so let's work on that. Let's look at some others. Okay, here's one. This is, I don't know what exam this is from, but this is sort of the second way that I can give you a question. And I worked one of these before. Let's work this one. I want to know the magnitude and direction of I3. And I've given you I2. I've told you that I2 is equal to 2.45 amps. And so if I want to know I3, well, to find I3, I'm going to look at this left or this right loop, because I have an equation that will only have one unknown in it. Let's start right here and go in this direction. So I have 12, positive 12, minus 2.45 times 2 minus 3I3. And then that's equal to 0. So that's 12 minus 4.9 divided by 3. So I3 equals 7.1 divided by negative 3. We get negative 2.4 or 37 amps. Negative 2.37 amps. And because it is down here, the answer.
I think it's not supposed to be a negative 3. It's just positive 3. Either both of them would be negative or both of them would be positive.
Did I make a mistake here?
Yeah, like whenever
Oh,
you
yeah.
thought about a negative,
Yeah, this should be negative right here, right?
yeah, either they're both negative or they're both positive.
Okay. Yeah, sorry about that.
Depending on how you manipulate it.
Yeah. So it'll be positive. So since it's positive, that means that my direction should be down, which is what it's labeled as, or what you would label it as. You could label it down or up, but if you labeled it as up, you would get a negative value for I3. Not that hard, right? Not that hard. Y'all could do one of these.
I'm not, well, I mean, you've already made clear that your definition of hard and our definition of hard are two different things.
No, that's not really true. That I think with practice that y'all can do this. I know that I've had many students over the years that are able to get this. So yeah, that's not really true at all. And besides, if it was easy, everybody would be doing it. It wouldn't really be worth that much, right? But it is hard. It's supposed to be difficult to master these things. All right, there's more equations here.
So where was that last equation down?
Why is it down?
Yeah.
Because I3 came out as positive, and I3 is labeled as down, so the current is as it's labeled. That you were correct in choosing the direction of the current.
I'm not quite sure if I understand.
Okay. You choose the direction for the current, and then you go through the whole process. And in the end, if you find that the answer is positive, then you chose the direction of the current correctly. If you find that the answer is negative, then you chose the direction of the current incorrectly. And you just switch it. You just give it the opposite answer.
So it's just sleeping.
Yeah, the positive doesn't give a direction. It just tells you, did you get the direction correct or not? All right? There's another one up here I'm going to look at. This one's a similar deal. In this one, I tell you that this current is equal to 2 amps. And I want to know what is I1. Well, I want to recognize that if I use this loop, I can calculate I1. That my equation would look like this. Starting in this direction, I would have minus 5 times 2 plus 15 minus 7I1 equals to 0. So that's, let me do it over here on the side. That's minus 10, that's 5 minus 7I1. So I1 is equal to 5/7. If an amp is positive, so it should be I1 to the left. I was just asking for, what's that, 0.7 amps. But I would expect the direction to, and the direction for I1 would be to the left. Because up here it's to the left. If you want to do, we have a few minutes, if you want to do a combination circuit, this will be the other type of question that you'll have on your exam. We've done capacitor circuits sort of in the last one, and many of y'all were here for that. But let's do the type of circuit that you'll expect for the combination circuit. We've done these in class, and it'll be one similar to that. So for example, it might be something like this. Uh-huh. It could be something of this difficulty. Now, it's different from the capacitor because the layout is, like, recognizing the layout is not so tricky. Like with the capacitor circuit, it's going to be laid out more like the ones that we did in the help session last time. Well, I don't say that it's tricky, but you have to recognize how to transform the circuit that I give you into one that looks more like this. But for your combination resistor circuit, it'll be something along these lines. 5 or 6 resistors in series and parallel. I'll try to make it easy as far as the numbers go. Let's see if I can just make up one. Oh, let's make this 3 ohms. Okay, so something like this. And I want you to be able to tell me what is the equivalent resistance. First of all, you have 2 questions. What is the equivalent resistance? And then what is the voltage or potential on any one of the other resistors? So for example, let's just take what is the current on that resistor. So we'll say what is I on the 4 ohm resistor, for example. But in the course of that, it's going to be one of these. Well, it's going to, in the course of finding that current, then you should be able to find the current on any one of the other resistors. So first, let's just do the equivalent. And I'll start with this. 2 and 4 is 6. I'm going to draw every intermediate circuit. You probably don't need to do this for the exam if you've been practicing, but if you need to, that's fine. I have 3, 6, 3, 2, and 2. Then I can do these 2 branches of circuits. There's my 3, and then those 2 will become new resistors. A 6 and 3 in parallel is 2, and a 2 and 2 in parallel is 1. So now I have a 1, 2, and 3, and so the equivalent resistance is 6 ohms. I have 12 volts across that, and now I start stepping back. I know that I have 2 amps because I is equal to V over R. That's 12 over 6, which is 2 amps. So I know I have 2 amps going through that equivalent resistor. That means I also have 2 amps here. Now, for each of these, V is equal to IR. So to find the voltage across each of those resistors, I would say 2 times 3 is 6 volts, 2 times 2 is 4 volts, and 1 times 2 is 2 volts. Now just do a quick check. 6 plus 4 plus 2, that's equal to 12. That's good because I know that my battery has 12 volts. Now, keep stepping back. I know I have 6 volts here. Because resistors in parallel have the same voltage and the same voltage as their equivalent, then both of these will have 4 volts and both of these will have 2 volts. Almost done. I've gotten almost every answer. 2 volts, 2 volts, 4 volts, 6 volts. Now, what I have here is I have 4 volts across those 2 resistors. And I need to figure out what is the current through the 4 ohm resistor. If I take just this little section, it is a single resistor of 6 ohms with 4 volts across it. That means that my current is equal to V over R, 4 over 6, or 2/3 amps. And that would be the answer. I have 2/3 of an amp going through here. So I have 2/3 of an amp here and 2/3 of an amp here. Because resistors in series have the same current. Now, if I want to know the voltages, I can find the voltages. V is equal to IR. So 2/3 times 2 is 4/3. 2/3 times 4 is 8/3. 8 plus 4, 8/3 plus 4/3 is 12/3. So that's equal to 4 volts. Those add up. These voltages add up to equal to the 4 volts that I know is across those 2 resistors. Gonna have a circuit like that. It'll be worth 2 questions. So, I try to give you this normal layout just to make sure that you can handle these combination circuits. But it'll be worth 2 questions because I'll ask you first what is the equivalent resistance, and then I'll ask you what is the current or the voltage on any one of the resistors. And it'll probably be one of the embedded resistors like that, where you kind of have to work through the whole thing to figure out what is that voltage or current, just like here. Like we really had to do the entire problem before we could ever figure out what is this current. And it'll probably be along those lines where you have to work through the whole circuit. That one, if you look back at some of the old tests, you'll find problems that are similar to that, okay? So it's not like this is a more difficult problem than you would have otherwise. It's about the same. In fact, the whole test is really of the same difficulty, even with the free response. I'm just giving more weight to these more important questions. Okay? What else? Anything else you want to? Yeah.
What would be the exact answer for the second question?
The second, for the current in the 4 ohm resistor, it would be that it's equal to 2/3 of an amp. Usually in these combination circuits, we don't give a direction because the current is all going in the same direction. It's all going clockwise through that circuit. All right. By the way, look at this. Remember we said the loop rule applies? If I go in this direction, I have minus 2 volts, and I have positive 2 volts, so it adds up to 0. If I go through here, I have minus 4 volts combined, and positive 4 volts, so the loop rule is 0. Or I can follow a circuit through any closed loop. And electricians do this a lot when they're evaluating circuit diagrams, is that they have this huge circuit, and they want to find out just one little piece of information about it, so they can zoom in on just a single loop within that circuit and apply the loop rule and determine the current or the voltage or whatever it is that they want to find. And now you can do it too. Right? You will be able to do this. I know for some of you it seems a little foreign, but you will be able to do it. Right? Yeah? Y'all feel a little better? No?
No, but it's better than nothing. No, but it's tough to do.
Well, I'm available. We have a few days till the exam, okay? So I'm available to help you. We can, yeah, around.